EAS reactions in short. Okay, why phenol will give electrophilic aromatic substitution, and where on the benzene ring the electrophile is going to get connected. So what does this reaction means? Okay, this reaction means you take some certain things, okay, and those things actually are known as electrophiles. Okay, they are electron loving species, they are electron deficient species, and when you react them with the alcohols, the phenols, this electrophile is going to attach itself to the benzene ring. And where on the benzene ring, can you tell me, Arshan, with respect to OH? Any idea?
Yes, sir.
Yeah, so phenol, yeah, I'm going to tell you very quickly first of all, then we are going to get into the details. So electrophilic aromatic substitution means the electrophile is going to come in and get attached to the benzene ring, and the H plus will be removed from the position from where the benzene ring has attached itself. Anushka, is it clear? So Anushka and Rayan, where do you expect this electrophile to connect itself with respect to the OH group? Is it at the ortho, meta, or para? Where do you expect it to?
Para.
Para, yeah, para is one, and
Meta.
meta. Okay. Theoretically, we can have ortho, para, and meta, right? But practically, if you look, okay, the main products are ortho and para. Okay, I'm going to remove the H plus so that there is a H at every position which is not written. So I remove that H and bring in that electrophile in this way. Okay, so where I have attached the electrophile? Can you tell me, Arshan, Anushka, Rayan, where I have attached the electrophile?
Sir, ortho and para position.
Yeah, ortho and para position. Okay, so why is it so, that we are going to discuss? So first of all, let me be very precise, and that is phenol. You can write, all of you, phenol is ortho para directing. Okay, ortho para directing means it will divert the incoming electrophile to ortho and para positions, right? Is it clear? So these are the major products. Well, do we get meta also? The answer is yes, but that is very, if someone says ortho para directing means main ortho and para products are the major product. While meta is the minor. Okay, clear? Meta will be there, but it will be in the less amount. So why phenol is ortho para directing? That's the question. So can any one of you try to explain me? Yeah, Anushka, Arshin, Rayan, quickly tell me why phenol is ortho para directing. What's the reason? And how do we make out that the OH group, we can see with our eyes the electrophile, how we will know that the electrophile is going to attach itself to the ortho position or para position. How the electrophile will know that? Okay, that's the question. Yeah. Any idea? So we need to look at the way in which the electron density get distributed on the benzene ring. Okay, so how this electron density get distributed on the benzene? Let's see this. Okay, so if you look at the oxygen, there are two unshared pair of electron lone pair, and you know these lone pairs are ideal pair of electrons which are actually not participating in the bond formation. Okay, and there is a loose electron, there is a pi electron density. These double bonds, the single bond is very strong, but the bond which is formed in addition to single bond is actually a weaker bond. That is the pi bond. Double bond, the single bond which is there in addition to the pi bond, the double bond which is there in the addition to single bond is pi bond. Okay, so this is pi bond. I have shown 2 electrons. So what happens is these electrons form a partial bond because they are sitting ideal and they participate in bond formation. Okay, so that they can attain more stability, and this is known as, this phenomena is known as resonance. Okay, is it clear? So what happens, these electrons try to form a bond with the carbon of the phenol, and the carbon can make only 4 bonds, and there are already 4 bonds, so I need to shift away, I need to pull these electrons apart and take them to the right hand side. Okay, so that we can have 4 bonds only, right? I will make a double bond at the upper position. Now oxygen will have plus charge. Okay, and these 2 electrons will come at the ortho position. Now this pair of electron which has come, which was earlier on oxygen, and oxygen has given its own electron, and that's why this pi electron has shifted on the ortho position. It will push the pi bond which is ahead of it in the same way it was pushed by the lone pair of the oxygen, and the pi bond which is ahead of it can get shifted to the para position. Is it clear? So this is how the electron density of the oxygen, lone pair of oxygen, is going to get mixed up with the electron density bonds of the benzene ring. Okay, phenol, and this can also shift ahead. Okay, is it clear? Anushka, Harshan, tell me.
Yes, sir.
So this is OH plus, and it can come again at its original position from where it started. Harshan, Ryan, are you getting what I'm trying to say? Okay. So this is actually the delocalization of electrons, because there are lone pairs which are not participating in the bond formation on the oxygen. These are known as lone pairs, the pair of dots which I have shown. And there are actually the pi electron, the double bonded electron, which were not as strong as the electrons of the sigma bond. Okay, so what happened is the oxygen tried to make a double bond, and while doing so, it has pushed away the pi electron density. Okay, and the pi electron density which has appeared on the ortho position and the para position. So you can see over here. So actually structure I have shown you one by one. Okay, just one by one. But actually electrons are not going to stay ideal. They will not sit at one place. Okay, so what I'm going to do, I'm going to write the mixed form of all these structure, and in which the electrons will move because they are moving in a circular manner on the benzene ring. So that's why I put a circle. The oxygen lone pair will also try to form a bond. Okay, that's why there is a plus charge. Okay, partial positive, partial negative. Why partial? Why not complete? Because if I take the average of all the structure, here it is neutral, here it is minus, here it is again neutral, neutral, neutral. So I will take the average charge. I will show on this complete molecule, and this is known as resonance hybrid. Okay, and this is the overall profile of the electron density of the phenol. Is it clear? Arshin, Ryan,
Yes, sir. Clear.
Anushka. Okay, so this is the overall profile, and this tells us that the phenol has now become more electron rich at the ortho and para positions. Okay, and this will help us to do the reactions. Okay, suppose if you take a phenol, and that's why the phenol was ortho para directed. Okay, for an electrophile. So if someone asks you why, how can you explain that the phenol is ortho para directing? You need to draw these structures. Okay, this will show you one by one that the electron density is increased at the ortho and para position due to the resonance. And there is one more thing. This oxygen has acquired a partial double bond character. Okay, because it is trying to form a bond. So it has formed the partial double bond character with the carbon. Clear? So because of this electron density, the reactions are going to take place at ortho and para position. For example, if you take dilute HNO3, okay, so where the NO2 group is going to come? Yeah,
Sir, it will be again on ortho and para positions, right?
Yeah, it will be at the ortho and para position. Right. Rian, is it clear? So what you are going to get? A mixture of orthonitrophenol and paranitro. Okay. Ortho and paranitrophenol. So orthonitrophenol will have low boiling point and paranitrophenol. And there is also a question that how you are going to separate them. Because ortho and para both are formed. Why ortho and para are formed? Because you have negative charge at ortho and para position. Okay. So if you heat them, this one is having lower boiling point. So it is going to form vapors very easily. Right? So it is going to come into vapors and the paranitrophenol is going to stay in the liquid. Is it clear? Let's talk about
Yes,
another
sir.
reaction. Okay. And the reason is also there is a reason. So, and you pass the steam through the mixture and that is known as steam distillation. What is steam distillation? So you separate two isomers by passing steam, okay, through both of them, through the mixture. Ortho one is having lower boiling point, so it will get into the vapor with the help of the steam, while the para is going to stay in the solution only. So which isomer is steam volatile? They can also ask you in this way. Tell me. Which isomer is steam volatile? Means which can go in the vapor with the steam. That is ortho isomers. Right? So why ortho can move out easily while the para is going to stay in the solution even after heating? The reason is very simple. If you write the detailed structure of orthonitrophenol, it will be like this. And look here what I have drawn, this dotted line. This dotted line is actually an attractive force between the H plus and O minus. H plus is hydrogen and O-, and this is known as intramolecular, means within the molecule the hydrogen bonding is forming. Intramolecular H bond. And because of this intramolecular hydrogen bond, the molecules are not interacting with their neighbors, the other molecules, and each molecule is forming its own hydrogen bond within. Intra means inside, okay, within the same molecule, right? And they are not forming the hydrogen bond with their neighbors. Okay. But what about the para-nitrophenol? Can you think of it? Arshin, Anushka, Rayan, tell me. Yeah, Arshin, what about para-nitrophenol? Rayan, Anushka.
So the bonds between them will be stronger, right? That's why it's not
Actually,
easily.
yeah, actually what happens over here is, yeah, that's true. But you need to tell what type of bonds. Exactly.
So the intermolecular H bond.
Yeah, that is intermolecular hydrogen. Actually, you can see over here is the OH and NO2 are far apart. And because they are far apart, they are oppositely placed. And oppositely placed, so if they are oppositely placed, they are not going to form a bond among themselves like the way in which we have seen the orthonitrogen. They are very far, they are opposite. So the OH is going to form, the H plus of the OH is going to get connected to the O minus of another molecule NO2. Okay, and similarly the NO2 will attract some third or fourth molecule. Is it clear? So that's how all the molecules are interconnected. So if the molecules are interconnected, and this is known as intermolecular hydrogen bond. Intermolecular means between two or more molecules. Okay. So that's why so all the molecules are connected to each other, and because they are connected to each other, the boiling point is going to be very high. You need to put in more energy to separate them. Is it clear or not? Tell me.
Yes, sir, clear.
Arshan. Yeah, okay, good. Yeah, so this is the thing. And why you need to take dilute HNO3? What will happen if you take concentrated HNO3 with phenol? Yeah, tell me. Actually, the phenol is very electron rich. Okay, and the electron rich positions are on the benzene ring. Are not all the positions are equally rich. Okay, the ortho and para positions are more specifically electron rich. Okay, clear? And so if you take concentrated HNO3 nitric acid, that will have more concentration of NO2 plus ions electrophilic. Okay, so the reaction is going to be more severe, and all the positions it will be up to the more extent, it will be in the more extent. Okay, and all the ortho and para positions, okay, will be replaced by NO2. So now the nitration has occurred at all the three positions. Clear or not?
Yes, sir.
So what this molecule is known as? Yeah, Arshan? Yeah. What this molecule is known as, what the name of the product? IUPAC name and common name? The common name is picric acid. And IUPAC name is 2,4,6 trinitrophenol. Clear?
Yes,
So
sir. Clear.
if you take concentrated, that's going to be, the reaction is going to be more. Similarly, we can talk about the halogenation bromination. Bromination is very, very common. So here also we have two options. One is if you take the bromine in carbon disulfide, which is a solvent oil like non-polar solvent, okay, or some organic solvent. Okay, organic solvent, this is just like oil, not like water. And you can do the bromination by taking bromine water. This is a polar solvent, more polar solvent, like because water, you know, water is much more polar as compared to your carbon disulfide. So here also we are going to notice a difference between the nature of the products formed. Yeah. So if you would have taken bromine and carbon disulfide, you will get either the orthobromophenol or parabromo. Okay. Mixture of both of them. But if you take bromine in water, the reaction is going to be more severe, up to the more extent, and all the three positions will be occupied by the bromine. So what's the reason? Anushka, Arshan, Ryan, tell me quickly, what's the reason for this? And the lower reaction is also considered as a test for phenol. Where you took bromine water, it will give white precipitate. So what's the reason? But here you have not taken concentrated or dilute, just you have changed the solvent. In one case, you took carbon disulfide, which was a non-polar solvent, just like oil, organic solvents. Many of the organic solvents are non-polar. And in other case, you took water, which is more polar. Okay. So what is going to happen in water? So in water, which is a polar solvent, means it can support more charges. That's what polar means. The phenol will undergo ionization. Is it clear, Arshan?
Yes,
Sir,
sir.
could you explain this again?
Yeah. Just time. So where ions can form? Can ions form in polar or non-polar medium?
Sir, polar.
Yeah. So if you put phenol in a polar solvent like water, you know, it can dissolve NaCl. All of us have seen. The phenol, if you dissolve it in polar solvent like water, the phenol will also breaks into H plus, just like Na plus and Cl minus. it will break into H plus and phenoxide ion. This is phenoxide. When it can happen? It can happen only if the solvent is stabilizing both the H plus and phenoxide ion. And when the solvent is stabilizing the H plus and the phenoxide ion, if it is polar, water like NaCl, water breaks NaCl, and that's why NaCl becomes solid. Okay, so why it happens? Because this bond oxygen is electronegative, it pulls away the electron pair from the H plus and the H plus departs. It is due to the acidic nature of the phenol also. That also we can say. But the main thing which is responsible is not the phenol only, but the solvent. The solvent actually is responsible for stabilizing this minus and plus both. As a result, the phenoxide ion forms and the H plus forms and the phenol ionizes. And this phenoxide ion, you know, phenol was neutral. Okay, and just now we have drawn the resonance structure of phenol. Just now. Look here. Okay. And the same thing you can do for the phenoxide ion also. It is the negatively charged ion which has formed by the departure of H plus from phenol. Same thing you can do. Okay, but one thing which you can realize over here is that the phenoxide ion is more electron rich. Why? Because it is O minus. In phenol, it was just OH. Okay, and it is O minus. So if it is O minus, it can give its electron density, it can push away its electron density towards the benzene ring more strongly. Okay, so one thing which I cannot draw here, but you can feel that the O minus is going to be more electron pushing as compared to the neutral OH of the phenol. So in phenol also we have drawn the resonance structure, in phenoxide also we have drawn the resonance structure. But the negative charge is going to be of the more intensity on the phenoxide ion. Is it clear to everyone? So same thing, same type of resonance structure we are going to draw, but phenoxide ion is more stronger, O minus is stronger electron donating group as compared to the neutral OH, and that's why the phenoxide ion is more electron rich as compared to the phenol, and that's why it is much more reactive. Though all the structures are, all the things, all the features are same. Okay, almost all the features are same. The difference only is of the O minus and OH, and this O minus is going to make the ring more electron rich at ortho and para positions. And if it is going to be more electron rich, what is going to happen? The reaction is going to be more severe. It is going to happen by in a more extent. Is it clear? So same
Yes.
structures you can draw, but you need to understand that this is more reactive in water. So phenol in basic medium, in water you can write, in basic medium also this is going to happen. In basic medium also, NaOH, if you would have taken, the NaOH will take away the H plus and the phenol will form phenoxide ion. So wherever you have water and basic medium, you will have phenoxide ion, and that's going to be more electron rich at the ortho and para position. And in the case of bromine, you have observed that the reaction has occurred in more amount by more extent. And how you can realize that? Because the bromine has attached itself to all the three positions. Okay, so I hope this is clear. Any doubts you can ask me.
No, sir, no doubts.
Arshin, Ryan. So this phenoxide ion, yeah, Arshin.
No, I just said no doubts. Sir.
Okay, good. So this phenoxide ion actually is it is not there only on this, okay, in this reaction, but in many other reactions. Okay, because I'm not writing the all the structures you can write, they are just similar. Okay, you can move that negative charge to the ortho position, right? Now the other reaction is, which is a very important reaction, that is coal-based reaction. It is also known as coal-based Schmidt reaction. Coal-based reaction or coal-based Schmidt reaction, and that is you treat. This is also the reaction of phenol. You take phenol and in basic medium, you know, it will form phenoxide ion, sodium phenoxide. Okay, now you treat it with CO2. Okay, and what we are going to get over here? Yeah, tell me. This CO2 is going to get attached. Okay. How it has happened and why taking off CO2 has attached, taking off carbon dioxide has attached a COH group at the ortho position. Can any one of you explain me? Yeah. So first of all, we know that this is the phenoxide ion, and we know what's going to happen for the phenoxide ion. The phenoxide ion, the negative charge of the oxygen is going to come at the ortho and para positions, right? That we know. Okay. Is it clear? But
Yes.
we have more number of ortho positions. We have 2 ortho positions and 1 para position. Okay. So these ortho para will have negative charge and CO2. Now this is regarding phenol that you already know. Because ortho positions are more, I will take only this one into my consideration to get my major product. Look here, this is minus and I have taken CO2. Okay, CO2 oxygen is electronegative. Carbon will have some amount of little amount of plus charge. So this minus is going to join to the carbon plus. Okay. Now again we are going to discuss the same thing. The carbon is going to form only 4 bonds. So if the negative charge is going to connect with the benzene, okay, some bond has to move away. And which bond is going to move away? The pi bond, the double bond. One double bond will get shifted on oxygen and it will form O minus. So electrons are coming from the benzene phenoxide ion ortho position. But why O minus doesn't attack? Because O minus is not there. The more charge is there on the carbon, which is more stronger. Okay, so when the minus charge comes at the ortho position, that minus comes and join itself to the carbon atom of the CO2. And while joining it pushes away, because carbon atom of the CO2 already having 4 bonds, so the pi bond is going to push away. Okay, and what you are going to get? You are going to get this intermediate. Is it clear? O double bond, right? There are H atoms also, which were not shown earlier. Okay, but now I am showing. Okay, is it clear? Yeah. So now I am trying to show to make the structure more clear. Okay. So this is CO minus. Okay. Now what happens? We need to get back our benzene ring. Okay. We need to get back our benzene ring. And how we get back our benzene ring? If the H plus is removed, and this electron will get back into the benzene and it will form O minus again. Okay, so you will have O minus and CO minus. Is it clear? Now you take acid. So this is the same structure. Now you take acid, which neutralizes this O minus at this and this position. Okay, and you have OH and COH. Is it clear? So what's the name of the product which you get? Yeah. Anushka, what's the name of the product? Arshin, Ryan, can you tell the name? It is salicylic acid. This is the common name. Is it clear? This is the common name, salicylic acid. And if someone asks you the IUPAC name, COH is the principal functional group. So it is IUPAC name is 2-hydroxybenzoic acid. So this is benzoic acid. A benzene with COH group is benzoic acid. And there is 2-hydroxy. 2-hydroxybenzoic acid. Clear? So salicylic acid. This salicylic acid is very, very important for us. Can you tell me its importance? Yeah. It is used to prepare a very, very important compound which is used in medicine. I told you earlier. Yeah, Abdullah, can you tell me what's the use of salicylic acid? Anushka, Arshin, Ryan, what's the use of salicylic acid? Where?
Sir, I'm not sure.
Yeah, any idea? Little bit if you have. A medicine which we take in fever and when we have a headache. This salicylic acid is used for the preparation of aspirin. salicylic acid, what you do the acetylation. You do acetylation and you get a drug which is known as antipyretic drug, which is known as aspirin. Is it clear? So what's the structure of aspirin? Any idea? Yeah, Abdullah. Aspirin, structure of aspirin. Yeah, okay, I will. This is salicylic acid. Okay, COH. And you do the acetylation by taking acetyl chloride, or you take acid. This is acetyl chloride, which is acetylating agent, or you take acetic anhydride, which is another acetylating agent. Okay. Acetic anhydride is this one, CH3 CO OCO CH3. Okay, so acetyl chloride and acetic anhydride, any one you can take, or I'm writing on. So if you would have taken acetyl chloride, you will remove HCl. You take pyridine also. Pyridine is a base which absorbs HCl. Removes HCl. Okay. So if this H is removed and Cl is removed, this and this both molecules are going to join together. Or if you would have taken acetic anhydride, then also the H and OCOCH3 is going to remove. Okay. So you can use any one of them. The result is going to be same. Okay. This OCOCH3 and COH. This is the molecule of the aspirin. It is used as an antipyretic drug, analgesic, painkiller. When we have fever or headache, light headache, we use this aspirin. So what's the IUPAC name of aspirin? Tell me. Yeah. So main functional group is this COH. Okay. And this part we already know, this is benzoic acid. Okay. And that part is acetyl and oxygen. Acetylation we did by using CH3COCl or acetic anhydride. Okay. So this is acetylated oxygen. So the IUPAC name is, the common name is aspirin. The IUPAC name is so be careful. Actually, in the school practicals also sometimes the teacher asks. 2-acetoxybenzoic acid. Is it clear? So
Yes,
how we are going to prepare aspirin from phenol? Tell me quickly. Yeah. Phenol, first we are going to do Kolbe-Schmitt reaction. We take NaOH and react it with CO2. Okay. And NaOH CO2, that will give you salicylic acid. And on the salicylic acid, we will do acetylation by taking CH3COCl in the presence of pyridine. Clear?
Yes, sir.
Right?
Yes, sir.
2-acetyl benzoic acid. Yeah, Sahil, is it clear? Ryan? Okay. So this is the way in which you prepare aspirin. Okay. There is one more way. Okay. One more way to prepare this salicylic acid. So one is, I will write in short once again. You took phenol, you took NaOH and CO2. I will summarize the whole reaction. And that gave you, followed by acid. Actually, because you are having basic medium, so you need to take H plus H2 to convert that O minus to OH. And this is your salicylic acid. And then you, if you have salicylic acid, you do the acetylation by taking, just remember one thing, CH3COCl. You can take acetic anhydride also in the presence of pyridine. Write minus HCl because HCl will be removed by the pyridine. OCOCS. Okay. So this is one method. Kolbe-Schmidt. Kolbe's reaction. And this is acetylation. Okay. There is one more method. NaOH and CCl4. Okay. Here also you are going to get first followed by H plus H2. Okay. Here also you are going to get the same thing. Right? And then you are going to do. So this is another method. Is it clear? If you take phenol and CCl4 in the presence of NaOH, here also you are going to get the salicylic acid. And then you do the acetylation. Clear? Again, you are going to get the aspirin. Okay. So there are two methods. By taking NaOH and CO2 and by taking NaOH and CCl4. And that will give you salicylic acid. And if you do the acetylation, you are going to get acetyl salicylic acid. That's the common name. The IUPAC name is going to be 2-acetoxybenzoic acid. Yeah, Anushka, Arshan, Ryan, Abdullah, is it clear? Tell me quickly.
Yes, sir. Clear.
Okay. The other thing is, so there is a very similar reaction, the third reaction, which is very, very important. And that is similar to this one. Okay, similar to this reaction. And very basic reaction. It is there in all the examination, right from your CBSE level, basic level, every level. It is there in class 12. And that is Riemann reaction. Riemann reaction. Okay. So any idea what this reaction is about? And what we are going to get? Yeah. Anushka, Harshin, Abdullah, any idea what we are going to get? So one thing is sure, whether we know the reagent or not, because this is the reaction of phenol. Many of the reactions of phenol are in the presence of NaOH. Because the phenol removes this H plus and makes it phenoxidine, which is very reactive. And then you take CHCl3. What this CHCl3 is? Remember, if you take CCl4, you can write it in words. If you take CCl4, you will end up with carboxylic acid group. Okay. But if you would have taken CHCl3, which is a chloroform, Abdullah, Ryan, you will end up with an aldehyde group, CHO. So what the name of this, common name of this? Any idea? Yeah. This is similar to salicylic acid, but this is not an acid because it doesn't have carboxylic acid group. So what the name is? The initial part of the name is same. Salicyl aldehyde. Clear?
Yes, sir.
So remember one thing. If you are going to take CCl4, you are going to end up with a carboxylic acid. Okay, but if you are taking CHCl3, you are going to end up with an aldehyde group. So this is not an acid. Okay, this is the aldehyde group. So not salicylic acid, name is salicyl aldehyde. Okay, but this reaction is very, very important. The name, it is one of the most important named reactions asked in all the examination. Okay, and that is so we need to discuss the mechanism also because it is there in the NCERT also, basic mechanism details. So, and the mechanism you can make out very easily. So first thing is you have taken NaOH with phenol, and NaOH, you know why do we use it with the phenol? Okay, because the phenol H plus will be removed and you will have Na, phenoxide ion. And the phenoxide ion is more electron rich because of its O minus. It's more electron donating, and this minus charge will move in the benzene ring, and it will appear on the ortho position, para position. But there are two ortho positions. Two ortho positions, so we are going to do the reaction preferably at ortho position because para is one, ortho are two positions. So preferably we are going to choose for the formation of major product, we are going to choose ortho. Okay. So now who is going to react? That's the question. So though we have taken chloroform, but this base will affect the structure of the chloroform also. Okay. So this chloroform is like this, right? So NaOH is going to remove the H and Cl. In basic medium, the HCl will be removed from the carbon. And if HCl is removed from the carbon, what you are going to get? Carbon, Cl, Cl, and there is just the electron which H plus left on the carbon while coming out, that they are going to stay as it is. And what this is known as carbene. This is just an unstable intermediate, okay, which is going to form in middle of the reaction, not the fine, because it is having incomplete bond. You can see this is not having complete bond, so it want to complete bond by accepting electrons from the phenoxide ion. So phenoxide ion can give its electron to the carbene, okay, they will get connected, okay. Just a brief idea you need to have there. H plus was already there. Now I'm showing for the clarity. It was already there. H plus was there, but it was not written earlier. So carbon, once it accepts the minus charge, now the minus charge CCl2 will be there on the carbon, because this carbon gave its lone pair Urshan and this carbon accepted, so this became minus. Okay. Now in this carbon minus will accept H plus, and this will, because ultimately you need to get back to the phenol structure because that is very stable. So in between that carbene snatched away the electron density from the phenol, okay, and in the middle somehow we that phenol benzene ring structure due to resonance got disturbed, and now we are again trying to get back to the benzene. Okay, so H plus will be removed, the electron will get back to it. Again, you will have O minus. So O minus. And you know that in aqueous NaOH, what happens? Abdullah, can you tell me on alkyl halides, aqueous NaOH? Arshan, aqueous NaOH, Anushka, Ryan. What happens if you take aqueous NaOH on alkyl halides? OH minus is going to come in and displace the Cl. Okay. So this is what you're going to get. So I've written 2 OH plus which came in with the help of base, and the 2 Cl minus which was pushed out. You will have 2 OH group, and the water is going to, the 2 OH group on the same carbon are unstable. So ultimately you are going to have water removed and are going to have a doubly bonded oxygen and OH, right? After doing the H plus. So this is how the whole process works. Okay, but exactly you don't have to get into the fine details of the reaction. Just you can be little bit have a idea that how it is happening. So first of all, you took NaOH, the phenol, H plus was removed. That's everywhere. That is in most of the reaction. And the H plus of phenol is removed. Phenol actually become more reactive, because the H plus, once the H plus is removed, the phenol become phenoxide ion, and the O minus moves inside the ring more with more intensity as compared to the normal phenol, which is neutral. So you have 2 ortho positions and 1 para position. And if you are going to take an electron deficient species, okay, if you are going to take an electron deficient species, the minus is going to join itself to the minus from the ortho position, because there are two ortho positions, is going to get attached to that electron deficient. Okay, electron deficient species, like in nitration, was NO2 plus. In bromination, it was Br plus. Okay, in coal-based reaction, it was CO2. In CCl4, it was CCl4, which was attacked by the phenoxide ion, ortho position of the phenoxide ion. And now in the Riemann-Tiemann reaction, though we started with, listen very carefully, though we started with chloroform, but chloroform ultimately changed itself to CCl2 when the H and Cl were removed in the basic medium. So the electron deficient species, which is the electrophile, attacking electrophile, was carbene. And that carbene actually accepted the electrons from the ortho position of the phenol. It got attached itself. Okay, and so you were having 2 Cl left on that group, and you were having 2 Cl left on that group. Now are they going to Cl going to stay in the same manner? No, the base, the hydroxide ion, is going to attack again on those Cl. Remember we discussed reaction of alkyl, right, with aqueous NaOH, and we discussed that aqueous NaOH is going to displace the halide. Okay, and the OH minus is going to displace the halide. So OH minus came in and the Cl minus was removed. Okay, you were having two OH group connected to the same carbon atom, but two OH group on the same carbon atom, that is known as gem diol. They are unstable, and they remove the water get removed. Okay, and finally you have C double bond OH aldehyde group present at the position, ortho position. Okay, this is salicylaldehyde, right? Is it clear? Any doubts on this?
No,
Tell me. Yeah, little bit idea you need to have. So the another reaction is very simple. This is the most complicated reaction. And if you are finding difficult, don't worry, because almost all the students find it very, very difficult. Okay, and many are find it first time. It is going to be very difficult because it is not a direct reaction. Okay, it is actually a lot of things are happening, so no need to worry. It's difficult for all the students, right? Now let me talk about the reduction and oxidation of phenol. We discussed the alcohols, okay, and alcohol oxidation of alcohols, right? And though alcohols can't be reduced because they do not have double bond, so we need to discuss the oxidation and reduction of phenol. Reduction and oxidation. So any idea how we are going to reduce it? This is just a very simple reaction. You will take phenol. You will heat it with metal, very electropositive metal, zinc dust. Where else do we use zinc? Tell me. Zinc is a good reducing agent. Any idea where do we use it? Yeah, Arshan, Anushka. Yeah. In galvanization, you must have studied for the protection against rusting. Okay, so zinc is a good reducing agent. So if you heat phenol with zinc dust, what happens? Zinc will itself get oxidized and it will reduce the phenol to benzene. The question is where that oxygen has gone. That oxygen has not gone anywhere. It is taken by the zinc, and zinc has itself changed itself to zinc oxide. That's it. Very simple reaction, but very important. Clear? So we discussed a lot of methods for the preparation of phenol, like cumene hydroperoxide method. Okay, we discussed the Dow's process in which we prepared, we actually prepared chlorobenzene, and chlorobenzene was reacted with NaOH. Okay, and that gave us phenol. But how to get back to the benzene if you have one phenol? That's very simple. Most simplest reaction among all the reactions which we discussed in this chapter. Very simple. Just heat it with zinc. You will get zinc oxide and you will get benzene. So this is the reduction, removal of electronegative atom. And what about oxidation? How you are going to oxidize the phenol? Tell me. So phenol is actually very electron rich, that we know because we have just now seen the resonance structures in which the lone pair of oxygen was moving into the benzene ring at ortho and para position, the negative charge. So phenol was very electron rich, and one who is rich in electron can lose its electron. Okay, and if you react it with an oxidizing agent, sodium dichromate, which is a very famous oxidizing agent. I've shown you in the last class also, orange crystals. Okay, and if you heat the phenol in the presence of sodium or potassium dichromate in the presence of concentrated H2O, so the phenol is going to get oxidized. Okay, and one more oxygen is going to get attached at the para position, and this is going to be the benzocaine. This is not going to be the sole product. Because ortho position also you are having negative charge. That's what we discussed. Okay. So that also can get some mixture of other quinones where you have double bond O at the ortho and para, but not at meta. Is it clear? Clear or not? Any doubt in this mixture of other quinones? Okay, that also is going, we are going to get, right? So this is all about the phenol oxidation and reduction. So let's do one question for the practice so that we can revise all the things related to phenol. Suppose if you react phenol with OH, NaOH, what are we going to get? Just NaOH, nothing else. This is just acid-base reaction. Phenol will lose its H plus. This is base, acid plus base. We're going to get a salt. Salt is phenoxide. The salt of the phenol and sodium. Phenoxide and NH2. Okay. So this is acid-base reaction. And zinc dust. Just now we have seen that was reduction of phenol to benzene again. Okay. Br2 excess in the presence of water. Let us try bromophenol. 2, 4, 6. But that is only in the presence of water. This is white PPT. Okay. Let me tell you one more test. So this is a test for phenol. White PPT. You put bromine. Okay. Let me tell you one more test. Neutral FeCl3. Neutral FeCl3. Phenol will give violet color. With neutral FeCl3. Right? Clear? And what will happen if you react phenol with phthalic acid in the presence of concentrated H2SO4? You are going to get an indicator. Can you think of the name of the indicator which you studied in your junior class? Yeah. Any idea? Indicator, acid-base indicator, which has a name phenol and phthalic acid, both something phthalic and yeah. Any idea? Arshin, Ryan, Anushka. Any indicator? Yeah, phenolphthalein. Clear? So have you heard of phenolphthalein?
Yes, sir.
Yeah. So how you are going to get? Just a quick. So this is phthalic acid. Okay, and this is phenol. Very simple reaction. This is phenol. This is another phenol. Okay, 1 mole of phthalic acid reacts with 2 phenols. Okay, and the water is going to get removed. Okay, so you have phenolphthalein. No need to get into detail, but just you need to remember it a little bit. Sometimes it can come. Is it clear? This is phenolphthalein, which is used as an indicator, acid-base indicator. Okay. Right. Now we move to the ethers. Any doubt in this, Arshan?
Sir?
Yeah. So this, just remember it. So this is also a test for phenol. Now the next is we move to the ether. So ether preparation. How you are going to prepare ether? So what are ethers? First of all, tell me. So alcohols were having, on one side you were having alkyl group, another side you were having H, and the ethers were having 2 alkyl groups. Okay, on both the sides. And that's why the ethers are actually very volatile. They have low boiling point because the alcohols are actually connected to each other. The H plus will get attracted towards the other oxygen. Okay, so there will be H bonding in it. Okay, so alcohols have higher boiling point and the ethers have low boiling point. Ethers are volatile. How you are going to prepare ether? Any idea? So that is by Williamson ether synthesis. Okay. So what you take in Williamson ether synthesis? So you react two things. And what are those two things? You take an alkoxide ion and alkyl halide. What is alkoxide? Alkoxide, you can get it very easily when you just, today we have seen phenoxide ion. Okay. So phenoxide, you take phenol, you react it with NaOH, the H plus is removed. So you take alcohol, you react with NaOH, and you have that corresponding alkoxide ion. So it could be methoxide, it could be ethoxide. If you would have taken ethanol, that will be ethoxide. Okay. Clear?
Yes, sir. Clear.
So you take an alkoxide ion and you take an alkyl halide. So alkoxide ion, this is O minus and this is very unstable. This is reactive. So, and this alkyl halide, if you look at it in detail, the chlorine is having negative charge and the carbon is having positive charge. Okay, partial positive. So this positive is just like an invitation to alkoxide ion to come and join itself to the carbon. Okay. So carbon is going to come in and attack on this. O minus is going to come in and attack on this partial positive charge, right? And the carbon everywhere, wherever the nucleophile is going to come, it is in order to make space for its own electron pair in order to join itself to the carbon. It will push away some other group. So in this case, the group which is going to be pushed away, the one which is having the weaker bond, is Cl. Cl is a larger atom, it is going to be pushed away very easily. Okay, and this O minus is going to join itself. So can you guys tell me what type of reaction is this? Is it an addition reaction? Is it an elimination reaction? Is it a substitution reaction? Is it acid-base reaction?
Substitution.
Yeah, it is nucleophilic substitution reaction. Right? So the nucleophile is alkoxide ion. This is SN2, okay, the one which we studied in your alkyl halide chapter. This is substitution because one nucleophile is coming in and trying to form a bond. The other group has departed with the electron pair. Okay. So you need to keep one thing in mind. The alkyl group should be small enough so that it can be attacked easily by the alkoxide. That's the key thing for this reaction. Okay. And you're going to get all the answers if you have this thing in mind, that the alkyl group, the reaction is going to be very easy if you have alkyl group as methyl And if you have ethyl